Hello and welcome to another episode of The Identity Navigator. I'm your host, Rohit. Before we start the episode, the Identity Navigator team has launched its second cohort, and this is also targeted towards mid career professionals who have been impacted due to the shifts in IT industry. So, if any of you find yourself in an unfortunate situation regarding job, keep trying and also reach out to me and other folks in your network. For people who are fortunate to have jobs, please help others in whatever capacity you can. We all have something to give: time, coaching, reference, expertise. Find out how you can help. Maybe don't expect people to come to you. Reach out proactively and offer to help. I can promise that you would be richer by this experience. Now, let's deep dive into today's episode, where we look into the role of graph databases in identity and access management, and explore why they are becoming indispensable in modern IAM systems. For over 25 years, LDAP and relational databases have been the backbone of IAM. However, as the demand of IAM systems evolve, the complexity increases, particularly in cloud native and enterprise environments. It is clear that traditional databases are struggling to keep pace. It is time to introduce Graph database, a technology which is inherently suited for many IAM use cases. So, traditional IAM tools have been built on relational databases, benefiting from their consistency, transactional support, and query capabilities. However, as the scale and complexity of IAM system increase, particularly in cloud native and large enterprise environment, the limitation of relational databases become more apparent. This has led to the exploration of graph databases and NoSQL technologies, which are better suited to handle modern IAM needs, including dynamic access control, scalable architecture, and complex relationship or permission management. For quite some time now, traditional IAM or IGA tools have been built on top of relational databases, or commonly called as RDBMS, leveraging their structured approach to managing identities, roles, permissions, and policies. While this approach has served well for decades, it comes with certain limitations as IAM requirements grow in complexity and scale. Relational databases such as MySQL or Oracle database, PostgreSQL or Microsoft SQL Server are built around the concepts of tables, rows, and columns. IAM tools have traditionally mapped users, roles, groups, and permission to relational database tables. These databases provide the structure and transactional environment necessary for storing and managing sensitive identity data. Many of us who have worked on any IGA tool will be aware of a users table, a table that stores basic identity information about users such as user ID, names, email address, cost center, and passwords, which are often or should be often hashed. In many cases, additional attributes, example department or job titles, are also stored in the table, right? So uh, you would have user ID probably as your primary key, and then you will have username and password hash and email and department stored in this table. Then you would have seen something like a roles table. And IAM systems use roles to groups permission or entitlements. And this structure is stored in a roles table. And each role typically represents a job function or access level within the organization. Then you would have also seen a permission table. And this table defines the specific action or resource that users or roles are allowed to access. So these are actually entitlements, right? They can be imported from the target systems. And permissions might refer to actions like read, write, or execute on specific resources such as application, databases, or files. Then you would have a table for a user to role mapping, which has many to many relationship. right? And in most traditional IAM systems, user can be assigned multiple roles and roles can have multiple users. So this requires a many-to-many relationship between users and roles, which is typically handled by a join table for those who are familiar with RDBMS or relational databases. So you would have something like a table called as user roles, and that would have a column as user ID and role ID, where user ID and role ID would be primary key, and then you would have foreign key references in the user table and in the roles table. Similar to user and role mapping, you would also see a table called role and permission mapping. And roles can have multiple permissions, and permissions can be assigned to multiple roles. So this is also a many to many relationship. And as you would have guessed, that would also be handled by a join table. So you would have a table like role permissions, right? And you would have a role ID and a permission ID because these are the two entities that we are tracking. And then these two would be the primary key, role ID and permission ID, and then you would have foreign key references to your roles table and your permission table. So the relational model offers a number of advantages that made it an ideal foundation for traditional IAM tools. The biggest of them has been data consistency and integrity. Relational databases are built on strong ACID, which stands for atomicity, consistency, isolation, and durability. So these RDBMS are built on strong ACID properties, ensuring that data, particularly sensitive identity information, remains consistent and secure across the system. This is essential for IAM systems which require accurate and reliable management of access rights. Transaction supports. RDBMSs also offer robust transaction management. IAM tools rely heavily on transactions to ensure that changes to user roles, permissions, or attributes are correctly applied without conflicts, especially in scenario involving role changes or privileged escalations. Relational mapping. The relationship between users, roles, and permissions are easily represented through relational mapping using foreign keys or join tables, making RDBMS a natural fit for modeling hierarchical structures in IAM. And last but not the least is query flexibility, right? IAM systems are built IAM systems which are built on relational databases use SQL or structured query language, which allows for flexible and complex queries. For example, queries to find all permissions of a given user or check whether a user has access to a specific resource are handled through multiple table or multi-table joins, which are honestly pretty straightforward in SQL. Now, while relational databases have been successful for IAM systems, they come with a number of challenges, especially as IAM requirements grow in complexity and scale. So let's look at five of these challenges, right? Number one would be performance limitation. As IAM systems scale to thousands of millions of users and roles, relational databases often face performance issues. Joins across multiple tables to resolve user roles and permission can become slow and inefficient, especially when relationships grow complex or maybe recursive, example hierarchical roles or role inheritance. Number two would be inflexibility with hierarchical and dynamic relationships. Relational databases struggle with deeply hierarchical relationship or dynamic permissions, which are common in modern IAM systems. Think cloud. And for example, calculating inherited roles or dealing with complex access policies often requires multiple nested queries, which can degrade performance. Additionally, role-based access control, or commonly referred to as RBAC, systems often evolve over time, and the rigid schema of relational database can make it difficult to adopt to changes in access model or policies. Number three would be scaling challenges. Relational database can have difficulty scaling horizontally in distributed environments. IAM systems often need to handle high concurrency, especially in cloud environments where user access systems across multiple geographical regions. And as a result, traditional RDBMS architecture may require complex replication, sharding, or other techniques to scale effectively. Number four, or the fourth limitation would be, or the fourth challenge would be complex queries. As IAM systems become more advanced and support features like attributes based access control or policy driven access, queries become more complex. Relational databases are not well suited for such systems, where access decisions are made based on dynamic attributes and conditions rather than static rules. Last but not the least would be audit and reporting challenges. Tracking detailed audit logs, changes to access permissions, and other security related events can require additional tables and complex queries in a relational database, adding to the system's complexity. So as IAM system grew more sophisticated, many modern IAM tools are looking beyond traditional relational databases to more flexible, scalable data model such as a graph database, which provide better performance for managing complex relationships, users, roles, permissions, etc., and are ideal for scenarios like hierarchical role inheritance or dynamic access queries. And we're also looking at NoSQL databases, which offer flexibility and scalability, especially for managing unstructured or semi structured data in large scale distributed environments. These alternative databases architecture allow IAM systems to handle more complex, real time identity management and access control use cases that are difficult to manage effectively with relational database. Now, I'm not saying that any of these things cannot be carried out by a relational database. For example, uh, if you do not want to have pretty strict structure to your data in a large scale distributed environment, you can store JSON within your relational database table, right? And that JSON can have or not have particular attributes depending on what is the data that you want to store and in which row. But these are like bastardization of relational databases concepts. So things can be done and carried out, but is the system natively built for it is the question that you would have to answer for yourself. It's very much like a developer trying to build an OAuth system, which can absolutely be done, has been done, and many companies like Google probably would try to create their own system, right? But for a financial company, reinventing the wheel is probably not the best thing to do, and it is probably better to use out of the box OAuth features while implementing the authentication and authorization requirements. But we digress from the topic, and then let's come back to it. So the emergence of NoSQL brought a new language incompatible with ANSI SQL, or commonly called as SQL, right? While convenient for storing documents or key value pairs, NoSQL was not optimal for write operations and complex joins. Much of the business logic had to migrate from SQL stored procedures to worker processes, leading to issues like data inconsistency, lack of guaranteed transaction retries, and potential transaction loss events. And these limitations were tolerable for online stores but unacceptable for IAM solutions. So that is why NoSQL was not able to get as much traction in the world of identity and access management. But then, about a decade ago, graph databases began to gain traction, with some backed by major technology firms, commonly referred as FANG. They matured significantly and now offer advantages from both OLTP, which is a underlying technology constructs for relational databases, and NoSQL words. Graph databases can store JSON blobs, update internal references swiftly, like group membership, and provide degree of data sharding and replication. However, graph databases face challenges with GDPR compliance, geofencing, and private clouds. Many enterprises operate in both government and public cloud, often needing separate instances for different countries. These requirements introduce the need to reference objects in other databases, similar to foreign security principles in Active Directory domain services that points to user in other forests. So graph databases still have challenges, especially when we are talking about geographical challenges for privacy or compliance reasons like GDPR. So before we deep dive anymore, let's understand what is a graph database. So a graph database is a type of NoSQL database that uses a graph data model to represent and store data. In a graph database, data is organized in terms of nodes, edges, and properties, which is ideal for capturing relationships between entities. This model is particularly powerful when working with complex relationships and connected data, such as social networks or recommendation engines or fraud detection systems. Right? We'll come to this fraud detection system a little later. So, a graph database consists of nodes, right, which are called vertices, which represents entities or objects in the graph. This could be people, product, or location. Each node can store data in the form of properties, which is key value pair, similar to rows in a relational database. So think of this in a social network, a node could represent a user and it will have key value pairs, username, user email, user password. Then the second thing is that we have in the graph database is edges, or you can think of these as relationships, right? Edge node can store each edge can also store properties and often has a direction. Example, one node follows another. So if we think in terms of our social network example, an edge could represent a thread relationship between two users or two nodes. And then we have something called as properties, which are additional attributes or details about nodes and edges. For example, a node representing a user may have properties like a name, age, or email, while an edge may have properties like the date two user became friends. Now, how a graph database works is for data representation, instead of using tables and rows, a graph database organizes data as a network of connected entities, nodes, and relationships, which allows for direct access to connected data without the need for complex join operations. And the second thing is traversal. Queries often involve graph traversals, where the database navigates through nodes and edges to find data based on relationship. Traversing a graph is efficient for querying connected data. Example, friends. Finding friends of a friend in a social network is much more easier when this is carried out in a graph database rather than a traditional RDBMS. Or think about what are all the permissions that the user have. So it would be easier to map in a graph database. And that is why, if you look at any of the new ITDR or ISPM tools, uh, which are so many of them in the market today, you would see that all of them are representing the user access in the cloud in a graphical format, because that is the format that actually is easier to understand, easier to look at, and also easier to query. So the benefits of the graph databases would be fast querying for connected data. Since they are designed to handle data relationships directly, they are much faster than relational databases for queries that involves complex relationships such as finding a shortest path or identifying clusters or querying deeply connected data. Flexibility. The schemaless nature of a graph database allows for flexibility in handling evolving data structure, making it easy to add new type of relationships and entities without the need for rigid schemas. And then intuitive modeling, real world relationships such as social connections or organizational hierarchies or recommendations are naturally represented in a graph structure, making graph database a good fit for modeling complex domains or modeling complex permissions, as we just discussed in the case of ITDR or ISPM tools. So some of the use cases for uh, graph database, which are like obviously social network representing users, friendships, likes, and interactions. For example, Facebook uses a graph database to model connection between users. Graph database could also be easily used in a recommendation engine. Product recommendation based on user interactions, preferences, and product similarity. Example, Amazon or Netflix recommendation. Identifying fraudulent transactions or behavior by analyzing relationship between entities. For example, in banking or insurance systems, the fraud detection uh, is easier to identify if the entities are represented in a graphical manner. This is where the detection and response piece of any ITDR tool comes in if the access permissions are represented in a graph format. And then knowledge graphs, right? Storing and querying information in knowledge based systems like Google's knowledge graph. Also, it could be used in traditional IT systems like network and IT operations, where representing IT infrastructure and dependencies, identifying network vulnerabilities, or tracking changes in network is one of the requirements. Example of graph databases would be Neo4j, which is probably one of the most or the most widely used graph database designed for effective relationship or efficient relationship handling and complex queries. Obviously, Amazon cannot be left behind, and it has got its own version of a graph database called as Amazon Neptune, which is a fully managed graph database service supporting both property graphs and RDF, which is I believe stands for Resource Description Framework. So, for any of my uh, startup founders out there in the identity and access management space, look into Neo4j or Amazon Neptune if you're looking for a fully managed graph database. Or if you are an Azure enthusiast or a Microsoft aficionado, you could also look into Microsoft Azure Cosmos DBs, which have Gremlin API, which offers graph database capabilities for large scale applications. So, more suitable for an enterprise use case than for a startup, but depending on your preferences and your tool of choice, you can select any one of them and you will not go wrong. So, how do you query graph databases? You could use Cypher, which is a query language used by Neo4j designed for querying graph data effectively and efficiently by traversing relationships. Or you could use Gremlin, which is a traversal language that is part of Apache Tinkerpop used in distributed graph computing system. Or you could use SparkQL, where it is a query language based for RDF based graph databases, commonly in semantic web applications. So, depending on the database that you choose, you would be presented with a query language that is most suited for it. Uh, I believe the learning curve is not too bad. So, if you want to get started, I guess you could start with relative ease, and if you already know SQL, you already understand what goes into querying data. I don't think the learning curve would be too bad. So a graph database excels at storing and querying highly connected data by organizing it as graph of nodes and edges. It offers superior performance for use case involving complex relationships such as social network recommendations and fraud detection by enabling fast traversal of connected data. Now might have already made some connections, but I wanted to explicitly apply concepts of graph DB and map them to IAM requirements. Now, from a purist perspective, in the context of graph database, a hologram is not a standard term. However, based on related usage in distributed database systems or multi-master replication environments, a hologram could refer to a replica or copy of data or part of a copy of the data, right? That is synchronized across distributed nodes. It essentially refers to how data appears in distributed state, where different nodes may have different versions of the same data depending on how replication and synchronization are managed. So you would hear terms like escrowed export, pending import, synchronized, unapplied export, and unconfirmed export, which seem to describe the state of a hologram or data replication as it moves through different stages in a distributed replication or data synchronization processes. Right. So escrowed import, where are all these terms coming from? Right. So escrowed import, let's understand what this. The data has been exported from the source node but is held temporarily before being transferred to the destination node. The term escrow refers to holding something in trust or temporarily while waiting for further action. So, in terms of our system context, think about this. This might be used in scenarios where the system wants to ensure that data is stable or verified before allowing it to be fully transmitted to another node for synchronization. Or maybe you want to check if it is compliant with your GDPR policies, right? So, in the same lines, right? These are terms, but these terms have meaning. So, let's understand what a pending import would mean, right? So, okay, let's understand this. So data that has been received by destination node but is awaiting final processing or application, right? So data is pending because it has not yet been fully integrated into the system's active data set. So you might want at the destination node to carry out conflict resolution or version checking before you apply it to your local database, and that is why it is pending import. So based upon that, can you guess what does synchronized mean? I'm pretty sure all of us now are on the same page that this means that data has been fully synchronized between the source and destination nodes. You could also have states like unapplied export, where the data has been exported from the source node, but it has not yet been processed or applied to the destination node. So this would mean that the data has been sent, but the destination node hasn't yet acknowledged or applied the change. So think about network delays or system latency. Or you could have unconfirmed export, right? Uh, Export where the export success or failure is still unclear. So there is nothing fancy to it, right? These are just simple terms, right? And they describe different states of data replication or synchronization in a distributed system where data moves between nodes or systems and each node hold a hologram or copy of the data. So in a distributed graph database, example Neo4j in a clustered setup, these states could be part of how updates or changes in one part of the graph are replicated across multiple nodes to maintain data consistency across the cluster. Now you would know why I'm talking about it, right? What if you change a user's permission on one node and you have a distributed model? How would you know if the changes have been applied to the other node in the different geographical region? What are the different type of states of data replication? And think of this in terms of directories have also solved this in a different way, right? We have replication servers in context of LDAP directories, right? How one domain controller is copying data to another domain controller and things like this. So it is just a different way of solving the replication problem. And then building these replication challenges within your implementation of your identity and access management system. So you are intentionally using this replication challenges to your advantage. So using graph databases can significantly improve identity and access management systems by providing a more efficient, scalable, and flexible approach to handling relationships. Think user roles, permissions, and policy enforcements. IAM systems are complex, and graph databases are naturally suited to manage complex relationships and connections between entities such as users and roles and resources and access rules. So let's look at some of the ways in which graph database can enhance IAM systems. Obviously, efficient representation of relationships. Graph databases excel at managing and querying relationships between entities such as users, role, groups, and permissions, which are fundamental components of IAM. In traditional relational databases, modeling these relationships can require multiple join between tables, which bring inefficient as the complexity of the system grows. Graph databases, on the other hand, represent relationships as edges between nodes, allowing for much faster traversal and querying of connected data. So, for example, in an IAM system, finding which user have access to a specific resource or who has administrative right in a given department is much more efficient in a graph model because you can traverse the nodes, users, groups, permissions directly. Let's think of it in terms of RBAC and ABAC, right? In a graph system, in an RBAC model, nodes represent users, roles, and resources, and edges represents a relationship like has role and role has permission. This allows for easy query to determine, for example, all users who have access to a specific resource by simply traversing the graph from the resource to all roles and then to users. In terms of ABAC, a graph database can represent not just users and roles, but also user attributes, for example, department or location, and policies that govern access based upon these attributes. So, this allows for more fine grained and dynamic control as the graph can be easily traversed to determine access based on both relationship and attributes. Hierarchy and inheritance. IAM systems often includes hierarchy of roles, permission, and groups. And for example, a company may have organizational hierarchy where certain roles inherit permissions from parent roles. Graph database, now as we all understand, are well suited for hierarchical structure because they can naturally model parent-child relationship, allowing for efficient traversal to understand inherited permission and access rights across users, roles, and groups. For example, in a corporate structure, a manager may inherit permissions from a department head and so on. And a graph database makes it easy to trace these hierarchical permissions effectively. Now, complex permission queries. Graph databases allows for complex queries related to permissions and access control. For example, think of this. A common query in IAM system is which users have access to a specific resource via a certain role and through which organizational relationships. So these type of multi-hop relationship queries when users and roles and permissions and resources are highly efficient in a graph database due to the native structure of a graph. And additionally, circular dependency or loops like recursive relationships between users and roles can be more easily managed and detected in a graph database as compared to a relational database. So when I was working as an Oracle Identity Manager or OIM developer, it wasn't unusual for me to come across or even write queries which were like 20 lines or a page length, right? And they were so very common, especially while creating custom reports using BI Publisher, because there were just too many hops to provide users the level of insights they were looking for. And sometimes Creating these BI reports and writing these backend queries and stored proc was a specialized or full-time job because of the complexities and comprehensiveness of these queries that were. So hopefully we'll be able to simplify some of those if we use GraphQL in these cases. Obviously, access, compliance, and auditing in case of a security audit. A graph database can quickly determine all users with direct or indirect access to sensitive information by traversing through various access control relationships. Think about dynamic and real-time policy enforcements, right? So the dynamic, if a user roles has changed, the graph database can instantly update the access control relationship, ensuring that permissions are enforced in almost real time. This dynamic nature also allows automated policy enforcement by enabling the system to react to changes as they happen, such as revoking access when an employee leaves or when their role changes. As IAM systems grow in size and complexity, graph databases maintains performance, making them ideal for large-scale applications like federated identity management or cloud-based IAM system. I believe at one point when SailPoint was still up and coming and OIM was losing its market share, I believe that the speed or responsiveness of OIM had much to do with it. It was a system that could allow you to customize anything on everything that you or the business could think of. And that eventually, among other things, led to the downfall of OIM because SailPoint can do at that point, SailPoint can do things much faster and it was simpler to implement and it just did not have that level of complexity or the performance degradation that OIM had. And I believe in the next iteration, we would compare these modern tools like SailPoints and Savients and other tools of the world against a IAM system based upon graph databases. Last but not the least, let's touch upon that in decentralized access control systems like, let's say, blockchain based IAM system, graph database can represent the relationships between different users, credentials, and decentralized resources in a scalable and transparent way, right? So, a graph database and federated identity model, it could be anything like SSO, multiple IDPs, access policies, cross system relationships are actually very well suited for each other. So there are challenges with graph databases. Sure, right? We did touch upon geofencing and GDPR requirements and sharding that I did not go too much in detail, but those are worth exploring. According to me, graph databases can improve IAM systems by providing a more efficient, scalable, and natural way to handle relationships, access controls, and permissions. They are particularly suited for managing complex queries, hierarchical relationships, real time policy enforcement, and scaling large systems. The result is faster performance, better security, and more flexibility in managing user identities and access across an organization. I hope you found this episode as fascinating as I did while researching for it. Thank you for listening. I'm always happy to get your feedback. I always look forward to your feedback. Thank you for an amazing response to last episode. I'm really appreciative and it just made my day reading all of your comments. If you're new to the podcast, you can reach out to me via LinkedIn or you can email me at theidentitynavigator@gmail.com. Thank you for listening and until next time, this is Rohit, your identity navigator.